Hello, and welcome to our Exocarb project. This project relates to a renewable energy technology which can, if implemented, contribute substantially to our energy supplies and has the potential to be carbon negative. Over 90% of all our energy usage is derived either directly or indirectly from the sun. The only sources of energy of any substantial quantity not solar-based come from nuclear, geothermal, and tidal energies. Solar and wind energy sources are wonderful, but they have the problem of not being available at all times. Luckily, both solar and wind have a tendency to produce the most energy when demand is at its highest. Although we have advanced our battery technologies, it is not yet economical or practical to use batteries to store the energy produced by wind and solar on a power grid scale. The best batteries available today are lithium-ion, and it takes well over 200 pounds of batteries to store the equivalent energy in a gallon of gasoline. The only large-scale storage system in use today are hydroelectric plants coupled with pumps. When an excess of energy is available, water is pumped up into the dam, and when energy is needed, water runs through turbines to generate electricity. We have very few of these systems, and implementing this storage system on a grid scale is not practical. Biomass is stored solar energy. Plants are solar collectors. Plants pull carbon out of the atmosphere. Carbon exists in our atmosphere in the parts per million range. Plants, trees, and grasses are approximately 50% carbon by dry weight. Carbon can be thought of as a battery. In the form of carbon dioxide, it is a discharged battery. When plants breathe in carbon dioxide, they use the energy of sunlight they have collected to charge the carbon and exhale oxygen. Animals, insects, soil microbes, and fire consume biomass and use the charged carbon for energy. Oxygen is combined with carbon to release energy and returned back to the atmosphere as carbon dioxide. Virtually all of the carbon from the plants gets returned eventually to the atmosphere in the form of carbon dioxide. Oil, natural gas, and coal are prehistoric forms of biomass. Coal was made by prehistoric land biomass getting buried over, subjected to heat, pressure, and the presence of water. Similarly, oil and the majority of natural gas were formed by ocean biomass, mainly plankton and algae. Our energy comes from coal, natural gas, oil, and nuclear, with renewable energy sources accounting for 8% of our energy usage. Biomass energy usage is approximately 5 times that of wind and 50 times that of solar. Fossil fuel use is set to increase globally with the expanding economies of China and India. China is opening new coal power plants at a rate of 1 per week. The Asian Pacific region has doubled their coal consumption in the past 10 years and currently consumes 4 times more coal than the U.S. In the wake of the Fukushima Daiichi nuclear power plant disaster, the nuclear industry has had a setback. Germany has permanently ended their nuclear power generation. Japan has temporarily, possibly permanently, ended their nuclear power generation. Both countries are using coal to make up for much of what nuclear power had provided. Switzerland plans to phase out nuclear power in 2034. A low-cost, efficient means to produce carbon-neutral biocarbon as a coal alternative could help stem the tide of the staggering increase in global coal consumption. A process to change coal to gasoline and diesel has been in use since the 1920s. It was used extensively during the Second World War by the Germans to fuel their war effort. Today, South Africa and China are using this technology to produce synthetic gasoline and diesel from coal on a large scale, with India soon to follow. According to a study done by the National Academy of Sciences, we can make gasoline from coal at a cost of $1.47 per gallon. Previously, cheap petroleum made this process uneconomical in the U.S. The problem today is, however, that the gasoline produced this way has twice the carbon footprint of a petroleum-based gasoline. Gasoline made from biocarbon would be carbon neutral. Carbon, much like water, cycles into the atmosphere from the land and the ocean. There is a constant exchange of carbon going in and out of the ocean to the atmosphere. On land, plants absorb carbon from the air, and when they die, virtually all of the carbon and energy they have absorbed goes back into the atmosphere. This balance has been maintained until we began bringing up carbon from the subsurface in the form of fossil fuels. We do not have to abandon our high energy density carbon fuels. We can just hack into the carbon cycle and utilize the energy and carbon that normally would be released to the atmosphere by decaying biomass. Unlike fossilized biomass, fresh biomass has not been contaminated by subsurface mercury and sulfur. Our process, hydrothermal carbonization, uses the properties of water at high temperatures and pressures to quickly convert biomass into biocarbon. Hydrothermal carbonization, also known as wet pyrolysis, has 2 major advantages over dry pyrolysis. It can process wet, fresh-cut biomass and has a higher percentage of biocarbon output per unit biomass input. By using hydrothermal carbonization, we can make biocarbon efficiently, without mercury and very low sulfur. In a sense, hydrothermal carbonization is a time machine. It takes bulky biomass and condenses it into biocarbon, also known as biocoal, in a matter of seconds, as compared to the millions of years it took to form fossil coal. Biochar is a name given to biocarbon when it is used as a soil amendment. Biochar is a form of carbon sequestration since it is stable in soils for long periods. It has been shown to be extremely beneficial to plants in many ways with long-lasting effects. It reduces crop needs for fertilizer and water. The United Nations is looking into applications of biochar as a way to stop or reverse desertification in sub-Saharan Africa. Please click on the biochar link below for a detailed video on the benefits of biochar. Our plan is to develop this technology and make low-cost mobile biocarbon conversion plants that can go to where the biomass is. The goal would be to have this technology become just another piece of farm equipment. Instead of burning or letting the agricultural waste like corn stalks and corn cobs decay in the fields, we should process this material into biocarbon, which can be sold by the farmer as an additional source of income. Widespread adoption of this technology can greatly reduce our fossil fuel needs by producing clean carbon-neutral fuels. If the biocarbon is also used as biochar, we can increase the yields and efficiency of our farmlands as well as sequester carbon. By densifying biomass into biocarbon, we can economically transport it from the farmlands to various plants using mature technologies to make electricity, gasoline, diesel, jet fuel, or synthetic natural gas, as well as using biocarbon as biochar. In the U.S., we are currently using less than half of the available biomass. If we start using energy crops like switchgrass and miscanthus, it is projected that the available biomass can reach 1.5 billion tons per year by 2030. Look out your window. How many solar collectors do you see? Plants are self-replicating solar collectors which use carbon as a battery. Biomass is stored solar energy. Even in urban areas, yard waste from tree and bush trimmings, as well as leaves and grass clippings, can amount to sizable quantities. Los Angeles and San Francisco produce 1,800 and 600 tons per day of yard waste respectively. All of this biomass can be turned into biocarbon. Although the basic technology of hydrothermal carbonization of biomass has been around for a long time, it has not progressed far beyond the lab due to the availability of cheap oil and coal. We have designed, built, and run our own small-scale hydrothermal carbonization reactor. We were easily able to turn all forms of biomass, from grasses to wood, into biocarbon. Our reactor ran tests with pressures as high as 4,800 psi and temperatures up to 1,350 degrees Fahrenheit. From the test results we have obtained from numerous runs, we have been able to determine the pressures and temperatures where favorable reactions and reaction rates occur. With this information, we have been able to design a continuous flow reactor which will be capable of producing biocarbon at a rate of 1 to 200 pounds per hour, depending on the feedstock. With the information we derive from this new reactor, we will be able to design and build full-scale production units. Please visit our website for additional links and more information regarding this technology.